This is the chance now for us to just go through the material that you've done with me, and if you have any questions, then this is the chance to ask those questions. We're also going to show you the field work data. So some of you went last week, some went this week. So I'll show you that because you haven't seen that yet. But then after that, we'll just go through everything that I think you've done. And if there's a problem with anything, this would be the time to ask. Okay. So maybe first of all, I'll show you the fieldwork data. Which you'll find here on Blackboard. So it's under course content on Blackboard. So you need to look at this with the information you've got already, so the notes you've made, but also the information from the pre-field trip information. Remember, there was a big handout for you which asks loads of questions, and really they're the kind of questions that are going to be in the test, so you want to be able to answer those. We'll have a look at that as well. But it's split into the aquatic carbon fluxes, which everybody was aware of that you were doing, so you're measuring your discharges and then also taking your samples to measure the concentration. There's lots of things to be talked about that, which might be questions on, but this is the data. So calculating your discharge, dilution gauging of discharge, there's a document there to talk you through it, which you may have seen before. And there's a video as well showing you how you calculate your discharges. The data for doing that is there, but I've actually got the very latest data as well, because there's two groups that have gone out. What I've done is to take 3 of the sets of data, just 3, okay, but I picked 3. At the moment, I'm just looking at the data from yesterday, so I will update this file. So don't use this file today, okay, but by tomorrow you can use that file. I'll just have the best sets of data in there. So you know what will be in there for the dilution gauging. You're expecting to see conductivity against time, so you've got a baseline conductivity, and then it's going to go up, and then it's going to come back down. It's worked very well, really, in all of these cases, but you'll have 3 of those to analyse. And as I say, there's a video there which tells you how to do it. Obviously, the video, when it's showing you, isn't using your data, because your data is brand new. So don't worry, it's different data, but the process is the same. So you'll be able to work those out. And the dilution gauging data as well is there. I got the data from people last week, and I've just picked 3 of the data sets, so you don't have to look at all of them. When you look at this spreadsheet, tell you what, we'll just have a quick look at it, all right, with this. I don't know what's wrong with that. Let me find it. Can you open it?
No.
There's something wrong with the connection. Well, what I was going to do when I opened it was to show you that actually a lot of it's filled in for you already. So the thing that's missing, okay, so what you've got is your width, depth, and velocities. The velocities worked out for you, so I've done that because you had counts per second or counts per minute. I've worked out the velocity for you, so you don't have to do that. I've also worked out the areas for you, so you don't have to do that. All right? You do need to multiply the area by the velocity, and you need to add them together. So you do have to do that, but that's not very difficult. But the thing that's missing is the errors. So you need to propagate the errors, okay, which you've done in that small exercise before. On this document as well, you can see, for reference, here is the completed error propagation exercise. So you did that exercise, error propagation with the discharge. This is a completed version of that. So if you haven't done it, you can see how it's done. Okay, and you can just copy what's done there to propagate your errors. Okay, so if I did any more, there wouldn't be anything for you to do. Okay, so you'll have your data, width, depth, velocity. The spreadsheet's set up so it's calculated the areas for you already by working out the areas of triangles and rectangles. You don't have to do that. But you do need to carry the errors. The errors that you'll see are, there's an error on the flow meter, which is from the manufacturers. So the manufacturer, when they sell the meter, they give you an idea of the error. So it's a standard error. It's an error on the flow metering. We've put an error on the width and the depth measurement, which I think we've put as about 3 centimetres. So it's plus or minus 3 centimetres on your width and depth, which is quite often the case if the water's flowing fast and you're trying to read it off. So it's that kind of error, but we've come up with it. You could have come up with that yourself, what you thought the error was on a width and a depth measurement. Okay? But we've written it in, so everyone's got the same error. I think I've written it in as 3 centimetres. I think the day that you went out, the discharge was quite low, actually, so it was a bit easier to read it. So you probably could have got it plus or minus a centimetre, I think, quite accurately. But actually, we've put plus or minus 3. Okay? So you've got those errors, so you can put those in, but you have to propagate them. So you're multiplying an error on the width of 3 centimetres by an error on the depth of 3 centimetres, and you propagate that through. And so you're multiplying errors going across from width to depth, from width to area to velocity, multiplying together, and then you'll have a column of numbers for each of the panels that you've worked it out for. They have to be added together. Each of those will have an error. So you're multiplying errors this way and then adding errors that way. Okay, and that's fairly mechanical. You can choose to do that during the assessment if you want. Do it now, right? And then in the assessment, when I ask you what the answer is, with a confidence limit, you just look at your spreadsheet, you type it in, and you go home. All right? So a lot of the questions are like that. If you've done the exercises on Blackboard, then you just look at the work that you've done, you type the number in, and you go home. All right? There's not a lot of work to do in the test. So if you've been through the items in Blackboard, then you just look at the work you've done. What I'm looking for is to see that you've done the work. The test isn't really about testing you, it's testing that you've done the work. Okay, so there's some questions that are like that, and other ones, same as with Neil's, and you've seen them with me before, these jumbled sentence questions, which are just testing your understanding of something that we've talked about. So, there will be something. I said, write an essay on why standard deviation is the most commonly used measure of variability. And we had an argument, didn't we, about that? We just went through, followed the argument through. There's undoubtedly going to be a section of that argument written with words missing, and you put the words in. Okay? That's as close as I can come to telling you what's in the test. So that's the field data. Plus, excitingly, there's also the atmospheric carbon fluxes, which you all got a handout for before you went out. So you're measuring the aquatic carbon flux, which is perhaps the main thing you were doing, but also you looked at the atmospheric CO2 fluxes as well. I think the first guys that went out didn't actually do the measurements, but that's not a problem. We did the second time. But Is he going to let me open any of these? This is the document I'm talking about, so make sure that you've read through this. We did talk about it on both field trips, even though you didn't make the measurements. Explaining the flux, starting from measurements of concentration, knowing that we've got concentration as mass per volume, and we know that flux is mass per time. So to go from mass per volume to mass per time, we need to multiply by volume, which we're doing by having a chamber in which we're measuring the CO2 concentration. And then, because we need it per time, we need to make the measurements more than once, and we're looking at a change in concentration over time, and that's how we get it per time. And then it's explained what we've done. There's one alteration on this, which for the observant you might want to see, which is that I told you that the offset was 400 millivolts. Is actually 200 millivolts. Okay, you don't need to worry about it if you don't want to. But when you see the spreadsheet with the data in, and you wonder how the calibration's been done, turning the output in millivolts into parts per million, you'll see that this is what I've been using, and what was written there was 400. So some of you would have spotted that and you'd have complained to me, but it's meant to be 200. All right. So making these measurements, I told you to make a note of when you've taken them. What I've done, I've taken the data and I've taken 3 of the measurements and I've put those together for you, and I'll show you those. So there are 2 places. I know only half of you actually saw this, but there were 2 places where we made a measurement. We made a measurement of the CO2 flux on bare peat, so peat that had no vegetation on it, which, as we know and we talked about, is some kind of imitation of the future, if you like, bare peat. And then we also measured the CO2 flux on some peat that had grass growing on it. And the data is presented there as the raw data in millivolts, and then the same data calibrated into parts per million. And the calibration's done here. You don't have to worry about it particularly, but there's the numbers, so 0.2 volts rather than 0.4. So we end up with the calibrated data, and the bare peat is these set of 3, and the vegetated peat is actually this one, where there's actually a much faster rate of CO2 production from the peat that's actually got grass growing on it. Now, reasons for that, but when you've got the grass actively growing, it means there's carbon that's being exuded from the plants, and that carbon is actually much more labile, so it breaks down much quicker. So actually there's a much higher turnover of CO2 where you've got vegetation. When the vegetation is under sunlight, which it isn't in the chamber, when it's under sunlight, it's actually pulling CO2 in. But in the dark, there's CO2 being produced, and there's more CO2 produced actually where you've got the vegetation growing, because it produces fresh organic carbon from the plants, whereas the organic carbon in the peat is actually very, very old and very tired and worn out, and it doesn't break down really anymore. We talked about this in the field, and we compared that actually with some aspects of the geology. We talked about the sandstone being made of quartz, and actually the quartz material doesn't break down very much either. It's very resistant, so it's there, but it doesn't actually interact very much. And actually the organic matter in the peat is very old and very unreactive. So that's what explains this data. Now, you're actually asked to work this out. A mass per area per time, okay, to work that out. What I'll do, you can do that anyway, I'm sure, but I'll just add something to that spreadsheet of the data just to indicate how you do that, okay? Because there's different ways of doing it. We've got the for the bare peat, you do actually have replicate data, so you can put an error on it. But part of it is working out the gradient, really, and deciding whereabouts you're going to measure the gradient. I want everyone to do the same thing so you can come to the same answer. So I'm going to add something to this before you go ahead and do your calculations on it. Let me add something to this to make sure everyone does the same calculation. But you can see the way that you'd be working it out is we're starting off with background concentrations of CO2, which is somewhere around here, 385 parts per million. And then over 400 seconds, it's increased to 430 parts per million. So we can work out how much CO2, what the mass of CO2 is produced over time, because we know the volume of the chamber is 1.5 litres. We know that we've increased the concentration from, say, 390 to 430, so increased by 40 parts per million over 500 seconds. 40 parts per million in 1.5 litres give you effectively a mass, and you've got a time. Okay. With the bare peat, you have got 3 measurements, which is what you were told to do, and that's what was done, so you could get an error on it. On the grass, there isn't actually a set of measurements. There's only one, which is a bad thing. But we did let it run for a long time. We were doing other things. We didn't have enough time to make 3 measurements. But you can still use that. It just means you won't have an error on that. Okay. So I'll just add something to that, and then you can do a calculation, and then you'll have a number. So when I ask you in the test, give me the number, you can tell me the number. All right. All right, I'm just going to quickly go through each of these things just to see where there might be any problems. But I will point out to you, though, in this, that student height spreadsheet, which is the central part, the first thing we do is making measurement meaningful. And the central part to making measurement meaningful was this spreadsheet, and you had it to fill in and to do things to, but there's a complete version of it there. So it's done for you, all right? You've all done it yourself anyway, but you can compare it to this one or you can use this one. This is the completed version of that spreadsheet. So it's got all the diffusion stuff all written into it. So it's just there for you to use. So bear that in mind. So if you have any problems, then you can look at the completed version if you haven't completed it yourselves yet. So it is there for you to look at. So we're deriving measures of variability. Oops. This was the first appearance of that spreadsheet, so doing your frequency distributions. But if I were to ask you a question from that spreadsheet, the reality is the completed spreadsheet's there. There's just a couple of things on that spreadsheet where you're asked to change some things, okay, which is on the diffusion part. So make sure you understand what's going on there. Anyway. And there's a calculation on there that I expect you to do where you're looking at the concentration of metals in the seaweed and working out a confidence limit. So again, just make sure you've done it. If it's already, I don't know, if you click on the completed version, it might be that calculation isn't done for you because it's just a bit too much to just do that for you, all right? It might actually be done for you, I don't know. But just make sure you've done the things that are on there, all right? Because they're the kind of things that you'd be asked about. But just to, if you remember, what we did was basically we worked towards defining the standard deviation and why it's used. And then we moved on from that, eventually, Um, Yeah, to consider how we use the standard deviation, and so we define d values. So by using the standard deviation, we define d values that allows us to then set confidence limits. So that's to do with the area of the distribution that's covered by so many standard deviations away from the mean. Okay, so they're the sorts of questions. You know, I could ask you how many standard deviations away from the mean do you need to go in order to cover 95% of the distribution? And everyone would know that because it's 1.96. So I wouldn't ask you that. But you actually came up with your own statistical table, right, which was not at the resolution of one that you'd pay money for. But if you'd done it, as you meant to have done, I could ask you the same question, and the answer wouldn't be exactly 1.96. It's a little bit wrong, but that's what I'd ask you, wouldn't you know? That's what I'd ask you. So just make sure that you've done this, you've filled it in. It gave you the ability to calculate the probability of a 7-foot-tall student. Seeing as you've done a question on that, I can tell you I won't ask you the probability of a 7-foot-tall student. That's not in the test. Maybe an 8-foot-tall student. And then we moved on to something that you covered with Neil as well, but this was a very basic starting point for it, looking at the normal distribution and diffusion. And there's a particular task on that spreadsheet, the text box asking you to do something. And this was getting you to match Fick's law of diffusion, that being that the rate of diffusion is proportional to the concentration gradient, and showing that actually that does match to a normal distribution. That was on there. That's what this is about. There's a video there and everything, but you can see that I'm asking you to do something and give me an answer to this question. So as long as you've done it and you're familiar with your spreadsheet, if you're asked it, you just quickly go to the spreadsheet, change your number or whatever, and that's it. So it's just, you just need to have done the stuff. If you've done it, then... If you haven't done it, then you can do it during the test, and if you can do it quickly. But don't do that. Okay. What to do with errors is an important part of this, because the numbers that you're getting from the field work, the thing that you do have to do with them is to get the errors and propagate the errors, as I said. And the spreadsheet, which is the problem here, they asked you to solve, which is to propagate the errors for this exercise. It's done for you, as I said. The spreadsheet's there on that field, on the field data. I give you the answer to this if you haven't done it already. So, but that's where it is. Answer to this is in the field data, which I just show you all that. You all recognise that. On the Blackboard folder that's got the field data, there's this spreadsheet filled in for you about how to propagate the errors. Okay. I did say, this was your chance to ask questions, and as usual, I'm just talking away. But, please, as we go through these things, if there's something that's been bugging you, then you should ask. I've said something to some of you before, if it's bugging you, it will be the same for other people as well. So don't be afraid to ask. Okay. Yeah, so that student height spreadsheet is there, completed for you. Actually, just to go back. Yeah, this. Oops. We spent a lot of time really just to get to this thing, which is about comparing two numbers and drawing confidence limits. You really, really need to be able to do that. That's what a lot of the questions are going to be about. And, you know, in lots of ways, what I've been doing with you is to a degree kind of remedial. I know that you know all this already, and many of you will have put confidence limits on. It's just that I'm also aware that when it comes to doing your thesis, like lots of people just don't do it, or they do it wrong. So that's why I've just been beating you over the head with it a lot. And it would just be tragic if my beating you over the head with it made it worse. So just make sure that you can do this. So, I mean, I know I've said it thousands of times and I'm beating you up some more with it now, but you work out the standard deviation and then you turn the standard deviation into the standard error by dividing it by the number in the square root of the number in the sample. That's your standard error. So words that you've heard. Standard deviation, we know. Get it from Excel. Standard is the measure of variability. You turn that into the standard error by dividing by the number in the sample's square root of the number in the sample. But then the standard error, it's still not a confidence limit. The standard deviation wasn't a confidence limit. It was a standard deviation. The standard error isn't a confidence limit. It's a standard error. A confidence limit is when you take the standard error and you multiply it by the d value. Except we don't use the d value very often, do we? We use the t value because our sample's small. And once you've multiplied it by the t value, then you've got your confidence limit. So standard deviation, standard error, t value, confidence limit. And that's a meaningful confidence limit because what we're saying then is we're 95% confident that the real value is between here and here. If we plot the standard deviation, then all we're saying is here's our number and this is the standard deviation on either side of it, which is, you know, a useful thing to know. We can compare another set of numbers that have got standard deviations on them, and if they've got a smaller standard deviation, we could say that it's more likely to be the real answer over here. But it's not the same as saying we're 95% confident the real answer is between here and here. So that's why we just want to move through to giving a confidence limit. Is that enough on confidence limits? This isn't really very fair, is it? Is there any... Okay. Okay. This kind of information, which is like the more interesting sort of stuff, I could ask you about this, you know. I want you to understand the concepts of like what's good and bad about using this kind of method. So, you know, if you've read it, then if you see a paragraph about it, you'll be able to know what's right and wrong in there. Obviously, all the information's there anyway. The only factor will be if you haven't considered it at all, then it's like you have to read it all, think about it, and then try and answer. So, but if you've had weeks to read this stuff, if you've read it and thought about it, then it will be really straightforward. Same with accuracy, precision, and resolution. That's clearly the ideal kind of thing to ask you in a short answer, multiple choice kind of thing. So just be aware of that as well. Again, if you've read it, then you should be fine. Okay, now this task was to help you to understand and to do the exercise. I'm not going to ask you specific questions about this, so you don't have to worry about that. If you've done it, it's not a problem anyway, but you know, I know some of you might not have actually, you know, gone through and done the whole exercise. You don't need to. I'm not going to ask you specific questions about that, so I'm just telling you that. But doing it will have helped you to understand all the other stuff, but I don't need to. I'm not going to ask you specific things about that. Yeah, these, if you remember, were some presentations that you were looking through, and you had particular themes of those and some specific questions. So the fact that I said these are specific questions, make sure you can answer them, okay? And the themes were, to guide you in looking at those presentations. So, there could be a question about the general theme as well, but the specific things, really make sure you've got these answers to specific questions. And that's the same for both of those presentations. We talked about, I know we haven't, this section on hydrological measurement has been there all the time for you. We didn't talk about it a lot in class, but it was partly because we were going to see the instrumentation in the field. So I'd said to all of you that pressure transducers are likely to be the single piece of equipment that you're most likely to use in working in environmental consultancy. We went through that because they measure the depth of the water, which is one way, it's a proxy for measuring discharge in an open channel, but also it's a way of measuring water movement in the subsurface, or water movement in the ground, by measuring depth in boreholes, and pressure transducers are used for doing that. That's why it's most likely that that'll be the bit of recording instrumentation that you use more than anything else. And that fits with what we're saying here. There's a spreadsheet here, which is diver installation arithmetic. I said to you, when I showed you the divers, that's the trade name for pressure transducer. So quite often people refer to them by the trade name of diver, because that's a lot of the ones who use are divers. They're made by Schlumberger. Other brands are available, but the arithmetic's the same, but it's showing you how you would actually do the arithmetic of when you install one. If you remember, we said that they measure the atmospheric pressure as well as the water pressure. So one part of the arithmetic is that you need to subtract the atmospheric pressure. Okay, so there's that to it as well. And then mostly they're installed in boreholes. And what people are interested in is the level of the water in a borehole. But they need to know the level of the water relative to something else, because they're always going to make... If we're trying to understand how water flows in the ground, we want to know what the water level is here and what the water level is here. So we want to know the difference between the two. And in order to be able to carry the difference between one and another, when we measure the level of the water in a borehole, we want to always refer that to ordnance datum, chart datum, or sea level. Okay, so it's referred to a standard level, and then everything is calculated away from that. So if you imagine you put a transducer in a borehole and you actually want to relate it to the sea level somewhere, then there's just a little bit of arithmetic that you need to do. Because boreholes typically, they go in the ground like this, but they stick out of the ground a bit. And then you attach your diver. You need to get it out of the ground, so it's on a piece of string or wire, and you know the length of the wire, but the wire's coming to the top of the casing of the borehole. And actually the transducer, you want to find the depth of the transducer, not relative to the top of the casing, but actually relative to the ground. And then the ground, you need that to be relative to sea level. Okay? All I'm saying to you is, if you look at, let's see, maybe it'll let us download it. There we go. Okay, there's a big text box there that explains it, and the things you're aware of is the diver, which we saw in the field, the barometric diver, which is recording the atmospheric pressure at the top there, and then the measurements that you can make when you install one. All it is doing addition and subtraction. All right, the best thing to do is just to look at this. The goal is to record water level relative to a reference. That's the important point. You know, I've talked about measuring the water level in a borehole, but it only means something if it's relative to something else, relative to a known reference. Same way that we make a measurement and compare it to a standard, same thing. The diver records the pressure of the atmosphere and the water. The barrow diver records the pressure of the atmosphere only. The diver reading minus the barrow reading gives you the depth of water above the diver. So that's the depth of water above the diver. So we need to know the position of the water surface relative to OD. OD stands for ordnance datum. If you're working, that's what people refer to, ordnance datum. If you're in the UK, ordnance datum is some little mark that's been chipped on a wall in a place called Newlyn in Cornwall. And it's sea level down there, okay? But that's ordnance datum. This is calculable from either the cable length or the dip meter reading. The cable length is because you want to have a cable. Your diver costs about £500, so you don't want to just drop it down a borehole. Goodbye. It needs to be on a cable so you can take it back out. So you've got the length of the cable or a dip meter. The bit of equipment that isn't a recording bit of equipment that you're most likely to use when you go to work is a dip meter, which is even less exciting than it sounds. It's a big tape measure on a reel with a weight on the end. And you're going to go to lots of boreholes in the rain, in the cold, and lower the dip meter down. It goes down on a big tape measure, spinning all the way down. It's got a metal weight on the end, so it goes down there. But it's got a little water sensor, very, very cheap water sensor on the bottom, and it goes beep. When it hits the water, it beeps. So you let the weight go down, you hear it beep, and then you wind the tape back until it stops beeping, and then you wind it forward a bit until it beeps again, and back, until it just stops beeping. And then you know you're at the water level, and you can read off the tape then. So that's a dip meter. Okay. Many of you will be using a dip meter. Well, I hope you are. I hope you'll get jobs. So you've got your dip meter reading, and these various things, and it's just a matter of doing some subtraction. Okay. So make sure you've had a look at that. And so, you know, if someone were to say to you, actually, the diver reading was instead of what's that? This is in centimeters. So instead of being 11.7 meters down to the diver, if it was 12.5 meters down to the diver, what would be different to this? So all you need to do is look at the spreadsheet, make sure you're okay with where these measurements are. They're all drawn on there and everything. So just have a look at that. It's important because if you go to work, I know, you know, not all of you are going to go into work where it's anything to do with contaminated land, but a large number of you will do. There's that sort of work. And these are the everyday tools of that job. And those of you that aren't going to contaminated land, you may well have to interact with people that do. And these are the tools they use every day. So if you're going for a job interview and you can sound as if you know what you're doing with these things, then it's a huge bonus, really, as far as getting the job's concerned. Whether you want the job at the end of it, with your dip meter, in the rain and everything, you don't have to do it forever. Yeah, this document is also reproduced on the on that field data spreadsheet. The document that you download that explains how to calculate your discharges from your dilution gauging is this document. You'll see that again there, but it's on the field data site, the field data folder anyway. It just explains how that's done. Again, there's a video which explains it as well. So, I mean, I could talk you through it, but there's a video that talks you through it. Okay, and I think we did speak about it, but just to be clear, like when you've done your dilution gauging, if you remember, you put a mass of salt into the water and you measure the conductivity downstream. You know that once the conductivity in the stream has gone back to the baseline conductivity, then that salt you put in has gone past. So intuitively, you should have a feeling that if you have recorded the conductivity during the whole period in which the salt was passing, then you should be able to work out the discharge. because the conductivity is a measure of concentration of the salt, and we know that concentration is mass per volume, and we've measured mass per volume over time during the period that the salt was put in. So just thinking about the units would let you'd be able to see that you should be able to work out, if you've recorded concentration continuously over a period, so concentration over time, you should be able to turn that into volume over time. Okay, because concentration over time is mass per volume over time. So you should feel that you can make that connection, and all you've got to do is manipulate the units to do that, and this just takes you through the manipulation of the units. So the missing thing being known, as long as you know the mass that you've put in. If you know the mass you put in, and then you measure concentration continuously during the period that the concentration is elevated, concentration is mass per volume, and you measure it over a time period, then you recognise that you could pull out of that volume per time if you know the mass. Okay, so that's the little conceptual thing. If you should be happy with that. And this just takes you through that and just asks you to rearrange the units. It rearranges such that, well, if you imagine, I think I say all this in the video, but there you go. If you imagine you've got a plot of time on the x-axis and concentration on the y-axis, and you've got something that looks like this, all right? The area under the curve is the summary of that. What we're after is going to be the area under that curve, okay? And we think, what are the units for the area under the curve? On the y-axis, we've got milligrams a litre. Granted, what you've measured was conductivity, but the conductivity can be calibrated to give you milligrams a litre of sodium chloride. So on this axis, we've got milligrams a litre, and this axis, we've got seconds. So the units then are milligrams a litre times seconds. Okay, multiply this by that to give you the units. Milligrams per litre times seconds. Okay, it's an unusual unit. It's not a unit that you use in everyday life. Milligrams a litre seconds. It's not milligrams a litre per second. It's milligrams a litre seconds. So it's milligrams a litre times seconds. And we know that milligrams per litre times seconds, on this side of the equation, somehow or other can give us meters cubed per second. Okay, and what you have to think about is how you rearrange those units in order to get meters cubed a second, going from milligrams per litre seconds. Milligrams per litre seconds plus the mass. What you have to do with milligrams per litre seconds and mass in milligrams to end up with meters cubed per second. If you write it, it says here, if you write it down and look at it, then you can figure out just how you need to do it. The result is that you've seen what you do actually. Oh, no, you haven't done it yet, have you? But it just takes you through how you rearrange it. It does say, if you divide the mass by milligrams per litre seconds, so if you've got mass in milligrams, you divide it by milligrams per litre seconds, if you look at it for a little bit, you'll see that what you'll get is meters cubed a second. All right, that's what's going on. So, as it says here, rewrite the above manipulations in order to understand them. That's the best thing to do. If you look at it, you'll see what's gone on. Milligrams divided by milligrams per litre seconds gives you 1 over seconds per litre, which is litres per second. Okay. So you can look at that. As far as you're concerned, in the mechanics of doing the calculation, I mean, I'm not going to ask you that because it's written down there, but I am going to ask you what the discharge actually was. So as long as you know how to divide the mass of salt you put in by the area under the curve, and the spreadsheet shows you how to do that, which you could do yourselves anyway, but I just taught you through that. You've got a column of data and working out the area under the curve. Remembering that the area under the curve, we're only interested in the bit that's the result of the salt being added. So what we've got this, but actually this rectangle underneath is the baseline concentration, and we just need to subtract that. So that's I don't want to say why it's complicated, because it's not complicated. But we've got this. We need to know the baseline and subtract the baseline area. So we just have the area under the curve. Again, it's all in the video. Okay. I think that really is okay. Okay, when we had the first part of predicting, a big part of that was just talking about the terms used in modelling. So you're going to be dealing with people that use models, and even if the only thing is that you're conversant with the terms that are used, that's a huge advantage to you. So, you know, given the fact that we just go on about certain of these terms, like calibration, validation, verification, just know what they mean, because again, they're just the sort of things that you get asked in this kind of test. And again, it sums up a lot if you do know what they mean. All right, and particularly the most complicated of those, and again, I think we went through an argument about this, which is a way to remember these things, is verification. If you understand verification, then you understand an awful lot of things. There's quite a lot to it. You know, verification is a, I don't know, I won't waste your time by asking you without, let's say, verification, you only do it when you use a numerical solution, if you remember, all right? So it's really important to us, because a numerical solution, why do we do that then? And that's because a numerical solution is always an approximation. So you should have these words just like in your head, like as a rhyme or a chant, right? Because they do rhyme. There is quite a nice little chant that we could come up with, but I'm not going to make you do that. But we have a numerical solution is always an approximation, so it needs verification. All right, and because it's an approximation, it's no use to us. Do you know, in the same way that we said about any measurement in the first place, a measurement to us is no use, right? And why is a measurement no use to us? The same reason, effectively, because a measurement is always an approximation, because we can't get it, well, as long as we talk about continuous variables, all right? For continuous variables, a measurement is always an approximation. If it's an approximation, it's no use, and it's no use because we don't know how approximate. If you don't know how approximate, it's just really there's no value to the measurement. So it's really important for us to know how approximate. The same thing with if we use a numerical solution will always be an approximation, and it's an approximation because we know that the true solution would require our problem to be broken into an infinite number of pieces, whether it's an infinite time steps or infinitely small grid size. That hasn't happened. Our numerical solution somehow is relying on breaking down time or space into pieces, which it doesn't exist in. So it will always be an approximation. Okay, so that's why we do verification. And then it also leads you on to how you would do it. We know that the true solution is infinitely small time steps or infinitely small grid size. So we know that if we make the grid size smaller or the time step smaller, our solution will be better. So we can test the solution we have. We can always test it by making a better solution. We make the better solution by making a smaller time step. The question's always then, the question becomes, how good a solution do we need to have? And that's kind of up to you guys. Well, it's up to the people that are going to be using the answer as to how good the answer they need to be. So you make the time step smaller, you get a new answer, and you have to decide, is the new answer different to the old answer? If it's not different, then we can stop. If it is different, we need to use a smaller time step, and we haven't verified our solution. Okay, so, but just being able to reproduce that as an argument will be useful for you in lots and lots of ways. So you should think that through. So that's largely what's come from this. You know, and it's written, there's particular questions. You know, it does say here, objectives, you should be able to understand what's meant by modelling, be conversant with the vocabulary. All right. And then we get on to the last section, which has probably got the most questions on it. So comparison of measurements we're happy with, really, because effectively that's confidence limits using the t statistic. Relationship between two variables. So again, there's an exercise. I'm not going to ask you specifically about that exercise, but doing the exercise is a very useful thing to have done. I'm not going to ask you specific questions. You're not going to pull numbers out of that spreadsheet. If you haven't completed this spreadsheet, it's not a problem, because I'm not going to ask you for numbers from that spreadsheet. But the exercise is well worth doing. If you remember, that exercise was developing a model of the relationship between concentration and discharge, and then developing the model and improving the model, and testing the model as you were improving it, testing it by using correlation and seeing how good the correlation was. And you went through several steps. We started out with a model that was a line of negative slope to becoming a line of non-linear negative slope, and we were taking logs of both sides, each time checking how we were improving it, and then eventually incorporating time dependence into the model. Very simple situation, but all the terms that we're talking about you would use again and again when you're talking to people about much bigger, more important models. But the same sort of process has gone on. We've gone on from an idea of something that was linear to something that was non-linear, doing a transformation of it, using logarithms, and then incorporating time dependence, and that makes it much more complicated. Okay, if you've gone through that. So be aware of those terms, but you don't have to have completed the spreadsheet. I won't be pulling numbers from that, but we'll be asking about the concepts, though. Right, and then we've got this spreadsheet calibration regression error. So this was recognizing that we look for these relationships, and then we actually use the relationships in order to make predictions. And we talked about the errors on measurements we make. We then use the measurements to build up a relationship. And we talked about propagating the errors. We need to continue using the errors. We've defined the errors on the measurements, and then we come up with a relationship. If we use the relationship to do another calculation, we need to carry the errors through that as well. And that's what this was about. But it says, how reliable are the relationships? First part of that was just calculating significance, so calculating p from your r squared, and that's really taking account of the sample size. We were saying that you can get a perfect correlation, always get a perfect correlation if you've got 2 points, because you can only draw a straight line between the 2 points. So if all you looked at was the r squared, you would think this is brilliant, because the number in the sample isn't part of Pearson's product moment correlation. So to bring that in, you need to consider the significance and calculate p. And quite often people don't do that. Mostly they do, but quite often they don't. And then there's a particular example working out the errors on a regression. I'm not going to ask you to work out the errors on a regression, but I do want to know that you've looked at the spreadsheet. Okay, because the spreadsheet, if you remember, was one where it takes you the calculation by hand to try and expose you to what's actually going on. And then there's another tab which shows it done in Excel. But again, if you look at the spreadsheet, there's a little part that's written in red, which might be the bit that you might have to change if there was a question about it. Okay, but do look at it. Understand overall that what's going on there is, we've talked about making measurements. We say there's always an error with the measurements. If we use the measurements to then define a relationship, there must be an error with the relationship. Okay, and quite often people don't consider that. This is showing you how you consider using the error in the relationship, because the relationship, in this case, it's how does ultraviolet absorption relate to organic carbon concentration, which actually matters to you guys now because you've been measuring organic carbon concentration from your samples. But there's a relationship between UV absorption at 254 nanometers and carbon concentration. But there's also an error on that relationship, and that's what this is about in this particular case. So if we're going to predict what the carbon concentration is by shining UV light through it, we'll come up with a number, but there should also be an error on it. Okay, and that's what that's about. So again, it's filled in for you. There's nothing for you to fill in that spreadsheet. It is filled in for you. And if you look through it, you'll be able to see there's a thing in there about you could change the sample number, or change the replicate number. That's one of the ways of reducing the errors. And there's an option in there of changing the replicate number, and you can see how the errors change. So just be conversant with the spreadsheet. All I'm trying to do is to get you to look at these things, and the test is just checking that you've looked at them. That's what it's about. Yeah. And then there's these compartmental modelling exercises, which really you do need to have carried out. Okay? So there's a video there to show how to do it, but make sure you've carried them out. And you can see that with some of these, well, all of them, they've got transfer coefficients in them. If you've got your spreadsheet set up, because you've done this, then if there was a question which said, what happens if you change this transfer coefficient, how does it change the outcome? Then you'd be able to do that. As long as you've filled the spreadsheet in, then it's just changing one number. If you change the transfer coefficient, how does it change the output? So I think you need to make sure that you've done this. Okay. The second exercise, which is, I mean, I'm sure many of you looked at it. I hope you've all looked at it. The second exercise is actually very similar to the first one, but slightly different. It's dealing in contaminated land instead. But I'm not going to ask you to pull any numbers out of that, partly because, well, I've kind of asked you to look at it here. But let's say there's not any direct questions on this one, but there might be on this one. Right? They're effectively the same. If you've done it, you'll see they're the same. It's the same model. It's just different starting values and different transfer coefficients. Okay? This one is related much more to pollution. This one is greenhouse gases. All right? But just to limit the amount of stuff that you need to do, but you can take it that I'm not going to ask you any direct questions on that. I think you can check that. But you do need to do this. Okay? Is everyone... This is a good point. How are you with that? Right? If you haven't, I mean, you've got another week anyway before the test, but there's a video telling you what to do here. There's a document there. So I'm saying is you do need to do this. All right? The thing is, like, you can't really have a problem with it yet if you haven't done it. So, because I was going to say, well, actually, how bad is that of me? I'm thinking you haven't done it. That's just terrible. Of course you've done it, because I said to do it. So, let's. What are the problems you've come up with in doing this exercise? I think that let's like maybe assume that some of you haven't done it. Okay? But if we assume that some of you haven't done it, then at least I can tell you it's a very carefully written document, compartmental modelling greenhouse gases from soils. Right? And that's why I'm a little bit shy of talking to you about it now, because it's written down there really, really well. Okay, yeah. But it is, and it's just, I really want to direct you to doing it, because a lot of things I've been talking about, like verification, all these things, you do them in this exercise, and you do them and feel good about it, because you do verification in 2 different ways, and it's all explained. So, I mean, I've got the feeling that maybe all the other things you've been doing, and you may well have done this, but, you know, in terms of what you need to do before next Thursday, do this. This will be... You need to look at the field trip data as well. That is definitely new. You've not seen that, but you know how to process it. But do this, and look at the second exercise as well. Like, I'm telling you, I'm not going to ask you a particular question on the second exercise, but it's there for a very good reason. You know, it's a real... I mean, I've had to change it from real data, but effectively it's real data. It sets it up. It is a site to the west of Manchester. It's dredging through the Manchester Ship Canal. It's real. It's a real contaminated land problem. So don't worry, I'm not going to ask you a question on it, but you really should look at it, because if you've done the one before, it's exactly the same technique, all the same things going on. If you've done the first one, then, in fact, I guarantee if you do the first one, you're going to look at the second one, because you can't get enough, right? That'll be the case, all right? So is everyone on board, at least, for, like, do that? I mean, I've got a feeling that you've done the other stuff, or you have done the other stuff. If you haven't done that, then do that. Then this next section was about methods of solution. What you've been talking about for the compartmental modelling exercise, it was a numerical solution using recurrence equations. And you also solved some very simple simultaneous equations. That's what comes out of doing that compartmental modelling exercise. I mean, many of you will have looked at more complicated models, but if you haven't, like, these are type examples of the sorts of things that people do, but they're the stripped down version that shows you what's going on. Okay, and a lot of these things are built around sets of simultaneous equations. You think about it, we come up with an equation that when we go through this modelling process, we make our abstractions and assumptions, and we formulate something into an equation. And quite often, it's not one equation, but a set of equations. So there's more than one equation that needs to be solved at the same time. That's often what the case is with these models. What they are is a set of equations. And the trick is to be able to solve them all at the same time. And there's a word for that, which is simultaneous equations, which you will have all heard of, right? But it's just solving equations simultaneously. And there's ways of doing it. In the compartmental modelling exercise, there's a pair of equations, because you've got 2 compartments. You've only got 2 compartments, compartment 1 and compartment 2. So it means you only have 2 equations. It's a pair of simultaneous equations. Those you can solve by hand. If you've just got 2 simultaneous equations, solving by hand isn't a problem. Okay? And in fact, for the exercise that I've directed you to, they're the easiest ones ever, because one of the equations has only got 1 term in it anyway. But anyway, so for a pair of simultaneous equations you can solve by hand. When you start to get more than 4 simultaneous equations, it starts to be quite painful to solve them by hand. And that's what these next 2 exercises are about. This is another compartmental model, just a generic compartmental model, and it's solved by inverting a matrix. And that's also what people do, but you don't have to do it. You press the button on Excel, and Excel will invert the matrix for you, and you can feel pretty pleased with yourself. Well, I feel pretty pleased myself with it. So just look through, but that's what it is. It's just another method of solution, and it means that you can talk to people about this, because that's what they're doing. You know, it might be useful to you, but again, this is what modelers are doing, inverting matrices. Just like Neil's been talking to you, hasn't he, about his data, and I'm sure what he's mentioned to is inverting the data. Yeah, he's talked about inverting the data. Effectively, it's the same process. Quite often you're inverting data sets, and this is an inversion. You'll find it useful. I mean, I used to do this at work, so the compartmental model that we showed you is contaminants moving in the soil, but you can also have compartmental models for the way that contaminants move around a human body. There's lots of work on that and toxicology, and you get a certain amount being in the liver and a certain amount in the brain, and there's transfer coefficients between each of these. So each of these compartments, you can imagine, if you like, as being someone's brain, someone's liver, someone's kidneys, and it's technetium that's moving around between them, and you can work out what the equilibrium concentrations are. Again, it's all written down for you. If you just fill in the numbers, and then you can say that you've inverted a matrix. The other way of doing it, which we have been over in talking about the groundwater modelling, which is the last thing we'll look at, is iteration. We talked about iteration last time, and that's really the commonest thing that goes on in these solutions. Effectively, you guess, you use the guess in your next round of calculations. So you guess, put your calculation in, then check it, and then change it, and you just circulate around. Iteration just means doing things over and over again. Have you ever felt like something's happening over and over again? But it shows the same data set solved by inverting a matrix and by iteration. Both of those processes being done in Excel. If you haven't done anything like that before, it's just really useful. That's why I'm telling you to do it, because the people you're going to deal with do this stuff, and you can talk to them then. If you have done this before, you'll think, well, actually, this is quite a small thing, but this is what's the central part. And then we don't, in the end, like, you're not going to, well, some of you will do, but not everyone's going to go away and be involved in constructing environmental models. You're more likely to be using environmental models or contributing to an overall big model. But in order to use them or contribute to them, you just have to have an understanding of what's going on inside of them. And to be honest, it's if you've not done it before, this is to make you feel unafraid and to put you on the inside, right, rather than the outside. There's no need to be outside to the people that do this sort of work, because it's not that clever. This is all that they're doing. If you do this sort of work, I'm not insulting you by saying you're not that clever, because it can be quite clever, but do look at these, and you should feel fairly comfortable with the iteration one, because we went over the groundwater modelling thing. I'm not going to ask you any questions on that. I'm not going to ask you to do anything. I'm not going to ask you to do any iteration or set a spreadsheet up or anything like that. So I won't ask you to do anything on those things, but do look through these methods of solution, though. Those spreadsheets, just be aware of how they're set up. So again, there could be a transfer coefficient that could be changed in that, and you'd get a different solution. What I am attempting to do is to make sure you've done the things I want you to do. So I think if you do the things I want you to do, then you become the people that I want you to be, right? and the way for me to do that, to get you to do the things that I want you to do, is to tell you they're being assessed, and I'm going to just ask you these questions on them. As I say, the test isn't about getting you to do things that are hard in the test. It's just checking that you've looked at these things. I want you to look at this, because I think if you look at it and you look what I've carefully written on it, then you'll get what I mean. If you read what I've written, you'll get what I mean. If you don't, then you should definitely ask me. But if you do that, then you'll get it, and you'll just be able to answer the questions. And that's why, really, you shouldn't be worried about this test. Right? As long as you've just read my stuff, look through that. Okay, right, I'm going to try again now. Who wants to ask a question about? And I'll tell you what, we'll just go back to the main heading, and right, you know the way that I work, which is just to say things over and over again. So it's another opportunity for me to say stuff over and over again, but we'll have a poll. we've got these, right? It's time to put your hands up. You can put your hands up for the section that I'm going to go over again, right? It's 4:45, so introduction to section 1. Any bits of making measurement meaningful? But you have to put your hands up for one, so there should be no embarrassment. Everyone needs to put their hands up for something in there. In making measurement meaningful, there's about 6 sections, aren't there? Okay. That's actually within there, making environmental measurement meaningful. Measuring. Okay. Predicting 1. I'm expecting a lot of hands at this point. Predicting 2. This has worked as well as usual. So, what can I do for you? How can I help you? Yeah, thank you.
Are you in office hours next week so that we can
No.
go through this again?
No.
So this is our last time?
This is it, yeah.
Okay, yeah. We were ready. But,
Bear that in mind. So what do you want to know? Come on, what can I help you with?
I think we're going to work it well, to be honest. Like, there's just going over about that one thing, people will need a chance to like go.
Yeah, well, that seems... That's what I would say to you. You just need to go through it, right? It's there, it's written down, and I guess that's really largely why, like, you know, if there's something wrong, like you think there's something wrong in what I've written there, then you should get in touch with me. That would be terrible. And I do things wrong, quite often do things wrong. Mail me if there's something wrong. I'll check if there's something wrong, and if there is, I'll let you know and let everybody know. It's just that we run into the fairness criterion now, in that it's coming to an assessment, and I can't really be giving individual tuition to people prior to an assessment. Like these are the sessions we've had in which we do the work, and you know, if you want to ask a question, you ask a question. There's time to do that, but now we're kind of going into, this is the assessment period, and we've got a week to run to get these things sorted. Yeah.
Just something that maybe we could do then, and I understand if you don't want to be sort of, you know, private tutorage because it gives an advantage, but maybe next week we can book a classroom like this and just have a study session, and I mean, if you can have that would be great, or we can just sort of organize something for students to help each other.
Yeah, you could do that. I have to say that was my plan for this session, really, but you know, at some point, you know, when I say ask me a question, we need to come up with some questions. So you can help each other out. I mean, I don't know what... You need to be able to speak up, like, what is it that's bothering you? Yeah.
I suppose the only question I have is, you know, when I look at the practice Q&A, that seems rather straightforward and, you know, I feel calm.
Yeah.
But then when you kind of just went over everything there, maybe that's going to be...
I'll tell you what I'll do.
Overwhelming.
Okay. I'll tell you what I'll do is I'll make sure there's another set of practice questions. Okay? Yeah. No, I did say that actually, and I should have done that already. So let me make sure there's a set of practice questions. Then maybe you'll feel a bit more comfortable about it. But there's things that you, like at the moment, like really, you should have done everything apart from the fieldwork stuff. So you do need to all look at that fieldwork data, which is basically the dilution gauging spreadsheet, the flow metering spreadsheet, and also the carbon concentration spreadsheet. So that all that data's on there, and largely what you need to do with that is just to propagate the errors on it. Okay. But yeah, I think the most important thing really is that I'll put up some more of the practice questions. But yeah, the things that you've seen are really what they are. So that's why, I guess, I don't want to say, like, don't worry about this, because, there's a week that you should spend fruitfully looking through all this stuff. But let me do that. I can also open there's a bulletin board thing on Blackboard, okay, and you can post questions on there, okay, I can just drop in and answer those questions. If we do that, then it means that everyone sees the answers, and that's fair. So let me do that. So then, if you have any questions, then put them on there. I think maybe when you've seen a few more practice questions as well, then you might feel more comfortable. You shouldn't really feel uncomfortable. I mean, in previous years, people seem to do very well. Not as well as Neil's, mind you, but yeah.
I think even that maybe more practice questions also for the geophysics side might be useful as well.
I'll tell Neil. I don't know if you can. Well, people generally do very well on Neil's. Yeah. I mean, people do well on mine, and very well on Neil's. So I think Neil's is probably not as daunting as you think, or if you think it is. All right. So, yes. Sorry. Yeah. Let me just say it again. Right. It's completely open book. So it's the 7th floor of the Simon Building over there. It's just a big computer lab with screens all around it, and you're sat behind the computer, and you can just look at whatever you want. Apart from you can't look at your friends, your neighbours, but anything that's yours, you can look at. So, all the stuff on Blackboard is there, all the spreadsheets, everything that you've done is there. So it's like I'm just testing you on like your completion of the workbook. Really, that's what it's meant to be. But you can look anywhere.
How many questions can we expect from your end?
Well, it's an hour. There's an hour of Neil's, an hour of mine, and there's a half an hour from the introductory week as well. I'll post a couple of questions like the introductory stuff as well, which they are just jumble sentence questions about concepts and some of them would just, if you've looked at explorable.com, you can just click onto that and you'll see that. But I will post, I think I've posted some. I mean, the questions that I've put throughout this are the questions that are in the test. They're exactly the same. Well, they're exactly the same questions, some of them. But yeah, there's 2.5 hours. You can choose to use them however you like, but there are 3 sections in there, and notionally it's an hour on mine, an hour on Neil's, and a half an hour on the introductory bit. But you can cut it up however you want to. And like with mine, I think there's 17 questions. Yeah, but they're just short answer questions or multiple choice questions. I don't know with Neil's, that sort of thing. It will say at the start like how many questions there are and what the marks are for them. And the way that the questions are presented, I think they're in random order. So each of you will get your questions in random order. But it says this at the start, and then it's just short answer, multiple choice questions. You did one with me in the second year, didn't you, Philip? Which you may remember. Was that dreadful? Yeah. I know it's easy for me because I write the questions but it is. All right. So if you look on Blackboard, tomorrow we have the updated field data and also somewhere for you to type questions. So it's a bulletin board thing. So anyone else that looks can answer the question as well. But if you can type the question, then you can answer it, and then everyone can see it. Okay?
How many types of exams multi-choice?
Sorry.
Choice.
Yeah.
And calculate
There's
the exams.
Yeah, there's some calculations, they're short answers and multiple choice.
So 3 types.
Yeah. Largely some of them will be, well in Neil's there'll be a calculation, but largely the calculations you'll be doing are ones that you've already done on the spreadsheet. For me, I'm asking you to give me a number from a spreadsheet that you've already completed. Okay, but that will be a number. A very important thing for you actually is to recognize the number of decimal places. All right, it will say on the question, but you need to do what it says on the question. If it says 2 decimal places, it's 2 decimal places. If it says 3, it's 3. If you put the wrong number of decimal places in, you won't get a mark. Okay, so I'll say that again. If you put the wrong number of decimal places, you'll get no mark. Okay, that's part of the test, right? You need to give the right number of decimal places. It will say that on the question. If it says give the answer to 2 decimal places, you need to give it to 2 decimal places. If you give it to 3, you'll get 0. All right? I'm going to say it again, right? If you give the wrong number of decimal places, you'll get 0. So if it says 2 decimal places, you have to give it to 2 decimal places. All right? It will say in the question, it's not a trick, it will say, but it's just one of those instructions that you have to follow. And it's important because it's a thing that demonstrates that you've got some idea about what you're doing. If you give the wrong number of decimal places, so quite often if you just take a number from Excel, it can have 15 decimal places, and it's ridiculous. It shows you you've given no thought to it at all. So it's not just to beat you up, but it's important. Like, you don't just give a number. In the same way we talk about having an error, but to give a number with 15 trailing decimal places just shows that there's no thought gone on. Yeah.
So sorry, in the question you're going to give the decimal places, or are we supposed to?
No. It will say. But it's just to be absolutely clear about it. If it says 2 decimal places, if you give 3, it will give 0. And it's the default thing. It will give 0. And I'm not going to change it. You know, that is the way it's going to be. So if you're unsure about decimal places, then you need to be sure. Basically, you know, the rules for rounding are what everyone needs to know. So if it says 2 decimal places and you've got 0.896, then we're going to have 0.90. All right. I know everyone's fine with that. It's just 1 year. Someone wasn't, and it was heartbreaking, but really I can't do anything about it. I've said, like, this is the way it is. So you just make sure it will say, don't worry, it will say the number of decimal places, but do give the right number. Okay. Yes?
Can I use the computer to search the internet?
Can you?
Use the computer to search the internet.
Yes, yeah. If you want to. You're sat at a computer. You can look on Google or anything else. It's not a problem. It's not very useful for you, but if you find that you're looking on Google, I think it means you're desperate. But you can do. You can look anywhere, apart from asking anybody else. Okay? But yeah, you can't ask anybody a question. Right? That's university rules, and you'll be thrown out of the university if you do anything like that. But you can use Google or anything. But Google isn't the answer. To answering these questions, Google is not the answer. Your spreadsheets are the answer. All right. All right. So look on Blackboard tomorrow for the final version of your field data, and also there should be a bulletin board thing that you should be able to access, and ask me a specific question and we can answer everybody.
You're putting practice questions.
Yeah, I'll put another couple of practice questions up as well.
Maybe you can include an example of spreadsheet order question. Maybe you can include one question from spreadsheet order.
Yeah, well, it might be a question about one of your spreadsheets. Yeah. No, there's practice questions. There's just the practice questions.